The last topic we have seen last week, on Monday, was interpolation, which is a fairly straight concept that you should know, because in engineering interpolation is used a lot, which allows to find some intermediate point between some other. And in computer graphics it is very important because in many cases, whenever you have some sort of images or some element you want to draw, you just have some endpoints and you want to find something in the middle, okay? And that's why it was important to refresh the concept of linear interpolation. In some cases you want to have several things equispaced, mainly the equispace point represents the pixel on screen that corresponds to one line or one edge of a triangle. So there are many cases in which interpolation is used to find whatever is in the middle, okay? And that's why we refresh that concept on Monday. Okay, so let us now move to the first topic, which is normalize the screen coordinate that goes in the direction of supporting several different hardware adapter and display and produce 3D generated images that looks the same regardless of the graphic adapter, the resolution, and the shape of the screen in which we are drawing. Okay, so current displays are able to use a different set of resolution. For example, today that I am connected to this beam projector, which is slightly different from the one we had on Monday. The projector, my operative system is working at a different resolution with an aspect ratio of 4:3, while on Monday it was working with a different aspect ratio and a higher resolution. All depends on the projector, so depending on the display, the computer will change the way the resolution and the number of pixels it has to draw on screen. Okay? If we are running a 3D application whose output will be included in a window, because our application is not again something meant to be full screen, the only things working at the time, but is meant that we have several things going on at the same time, then the user might change the size of the window, change the aspect ratio, and have everything to adapt in this way. Okay, so one of the goals for which we need this normalized screen coordinate is that application want to draw the same images with correct proportion regardless of the graphic adapter, the resolution, and the type of screen is connected to our PC. Okay, and normalized screen coordinate solve this problem. So, what can change from one screen to another? The first thing that can change, as I told you, is the aspect ratio, which is defined as the number of pixels that are, the size of the screen horizontally and the size of the screen vertically. Some aspect ratio, like the one that we have today, are 4:3. Some other, like the one that we had on Monday, which are more widescreen, are 16:9, but there are also now some much wider screen. You can see if you go in any electronic stores, a new monitor that have some aspect like 21:9, meaning that are much wider than high. Okay? Moreover, we might have pixels that do not have a square shape. For example, it was very common when monitor had the 4:3 aspect ratio to have one resolution that was the 1280 times 1024, in which pixels weren't square, but they were some rectangle which were slightly wider than high. Okay, so pixels weren't perfect square like in this case, but they were more compressed rectangles. Okay, but regardless of the aspect ratio of the screen and the resolution that we have, if we have a 3D application inside a video game, we want to show the same thing on different monitors, with the main difference that if we have an enhanced aspect ratio, we might benefit by showing some extra feature which won't be available in more compact display, but nonetheless we will have the same main feature shown on the screen, okay, regardless of the ratio. This became even more important if we want to draw the image in a window. So the aspect ratio is defined by the size of the windows we are going to use, and in some cases we are also rendering to memory to achieve some special effects, and in this case we might have whatever aspect ratio we wish and whatever resolution we want, depending on the quantity of memory we are using to write our image on. Okay, so how is this solved? If you remember, on Monday we have seen the classical coordinate system in which pixels are numbered from the top left corner, pixel 00, to the bottom right corner that has the coordinate which corresponds to the number of pixels horizontally and the numbers of pixels vertically, both -1. Okay, because pixels are indexed with an integer index. Instead, in normalized screen coordinate, the origin of the coordinate system is put in the center of our display area, in the center of the screen, in the center of the window, in the center of the video projector, in the middle of the area is going to be shown. Then, from this point on, the pixels have coordinates which are no longer represented by integer number, but they are represented by floating point numbers, and these floating point numbers goes from -1 to +1, both in the horizontal and vertical direction. Okay, so the lower left corner will always be -1, -1. The upper right corner will always be +1, +1. The lower right corner will be 1, -1, and so on. The upper right corner will be -1, 1, etc., etc. Okay. Note that in this case we have again the conventional orientation of the axis. So, while screen coordinate had the vertical direction flipped, as we said, due to hardware reason, because originally monitors were addressing the lines from the top to the bottom, this type of coordinates, which are meant to be independent on the device, are again oriented as the conventional set of coordinates that we use on paper. Okay, so the y-axis goes negative to positive from bottom to top. Okay? Okay. The conversion from normalized screen coordinate to the hardware coordinate is very simple. As we have said, the normalized screen coordinate go between -1 and +1. Sorry, here, -1 to +1. Okay, if we add 1, the coordinate will go, since x is from -1 to +1, y, once we add +1, this will go from 0 to 2. When we divide it by 2, the number will go between 0 and 1, and if we multiply it by the number of pixels on the screen, it will go from 0 to the number of pixels horizontally -1, which means the hardware coordinate that we've seen last time. Okay? Note also that since here the y-axis is flipped with respect to the hardware coordinate, when we go to the hardware coordinate, we have to switch the direction, so that what was at -1 vertically will be at the bottom of the screen, and what was 1 will go at the top. So instead of doing x minus 1 plus 1, we do 1 minus 1. So that since y go between minus 1 and plus 1, when we do 1 minus, it will go from 2 down to 0. Okay, exactly in the opposite. When it is minus 1, it will be 2. When it is plus 1, it will go to 0. So that when divided by 2 and multiplied by the height, we have the correct pixel coordinate. Okay, of course, this will be a floating point number of the pixel, while the pixel that we are using is generally an integer value. But with some special algorithms that are called anti-aliasing algorithms, which unfortunately we will not be able to see, the graphic adapter can find some point which seems to be in the middle of one pixel by properly shading the color of the surrounding pixel to the coordinate we have chosen. Okay? As we have said last time, the graphic adapter are usually co-designed with the driver that access them. User always decides the coordinate in this coordinate system, and it leaves to the driver the task of converting these normalized screen coordinates to the actual coordinates that can be seen on screen. Okay, so we never will put one pixel at pixel position 341 horizontally and 227 vertically, but we will always position one pixel with two coordinates that are between minus 1 and plus 1. Okay? Okay, so at this point you can already do your first assignment. So if we would be lucky, what happened? Okay. Are we lucky enough to have it? Yes. Let's hope that now that the course is started, it will work. I hope it works. If it doesn't, if you go to the computer graphics section of the big page, you will find some folder near the one where you have found the slides that now contains, no, it doesn't seem it is working, so I will have to show you on my PC. You will find this assignment 01, paint by number. If you open the folder, you will find one PDF that tells what you have to do. So basically, there is this WebGL application that is contained in this HTML page, index.html, that wants to draw a little house on screen. So if you get this index.html and you open it in a good web browser like Google Chrome, because Safari does not support WebGL, you will see this representation. Okay, so this squared paper that you see here is a representation of what a screen can be. And in this area, we are drawing things using normalized screen coordinate. Okay, so this is the HTML page. The drawing that now are these red cross and these red lines, okay, are all contained in this small file that is called draw.js. Okay, basically it calls 3 times the line command. Each time the line command is called, one of these lines is being drawn. So this first command 0.4, 0.4, minus 0.4, minus 0.4 will be drawing the line over here. This instead will be drawing the red line over there. And this last one is drawing this line over here. Okay, so this 4 number represents the x and y coordinate of one extreme of the line. The other 2 represents the normalized screen coordinate of the other line. The grid will help you, since it is a grid with a step of 0.1, understand in which point of the screen this will be shown. So your first assignment will be change this very simple line of code, and in particular change the normalized screen coordinate that you see here to draw with this red line over the small house that you see below. So actually the goal is modifying that to have this you can go to the recording and already see the solution, but that's not the point. I will publish the solution next time, so at least we haven't come to the lesson to know what to do. So you can come here and see which is the goal. Okay, so change the commands to have the small house over there. So instead of having just the 3 line over here, randomly paste on the screen, find the right coordinates to draw the house. Since this is very simple, there is also one advanced task that asks you to extend the exercise to not only draw the house, but also a chimney, a door, and 2 windows inside the house. Okay, so the goal of this extra part of the assignment, the first one is mandatory. If you want, you can also try the second part, and if you try the second part, you should have something like this. Okay, so basically, no, not this one, this is another thing, so the correct one is this. Now, what happens? Okay, sorry, I have opened the wrong file. Okay, so this is the correct one. So to the very simple house that you have here, try to add the chimney, the 2 windows and the door. The hardest part is the chimney. If you really want to draw the chimney like this, you have to use the interpolation to find this point over here and this point over there. Okay? Why there is also this narrower house? Just to say that this narrower version of the house uses exactly the same code. So what is written in this draw.js file is exactly the same, but in the wider house and in the smaller one. Okay? What changes is the window size, the area, the format on the screen where our code is writing. Okay? If we change the window but maintain the coordinate, this system will always go from -1, to 1, 1 with 0 in the middle, and of course, if we change the viewport shape, this code will produce something different. Okay? How we can make something that will also have the same proportion depending on the shape of the screen? This is something that we are going to consider later. Okay? But up to this point, it is important that whatever the shape of the screen is, using this normalized screen coordinate, we can access this. Okay? A corollary to this request, try to do this assignment. If you have a problem with this assignment, go away. This isn't the course for you. Okay? This is the simplest one. If you have trouble with this, whatever comes later will be impossible. Just to tell you. Okay? So this is very, very simple. Haven't you decided yet to follow this course or not? If you cannot do this, then probably you are in the wrong place. Okay? Okay. So, very simple. Let's try to do that. And of course, next week we will give something slightly more complex when we will be starting moving to 3 dimensions. Okay? Okay, so let us now continue with the next part. Okay, so we will start considering the 3D coordinate system. As we have said, the main topic of this course is 3D computer graphics, so let us see what can we do to have 3 dimension on a b-dimensional screen. Okay? Sorry. It is really too hot today and quite sunny. Okay, so let us start with 3-dimensional coordinate system. Okay, so we want to do 3D computer graphics. Whenever we have 3 dimensions, if for drawing a point or a line on a 2-dimensional screen, just to coordinate the x and the y are okay, if we want to show something in 3D, we need at least 3 numbers to define the position of one object in the 3-dimensional space. Okay? So we need 3 components. But for reasons that will be clear in the next few lessons, actually in computer graphics, the points in the 3-dimensional space aren't defined by just 3 numbers, a 3-dimensional coordinate system, but they are identified by a 4-dimensional coordinate system. Okay? So all the points we are going to put on screen will be characterized by 4 dimensions and not 3. Okay? This particular type of coordinates used to represent point in a 3D space is called homogeneous coordinates. Okay? And by adding this 4th component and use 4 numbers instead of 3, a lot of extra features can be done, and all the computation that must be done to transform something that is into the real world to something that is shown on the screen can be greatly simplified. Okay? So, x, y, and z is a point in a 3-dimensional space. I think that all of you that are here can easily understand why, but what might these 4 coordinates be and how it can be used? Okay, so the 3 position, x, y, and z, represents the position of one object in a 3-dimensional space. The 4 components, which is generally called w, because if you go, w would be the one before x in the alphabet, so it's the most appropriate to be put here, represents the scale, the unit of measure that is going to be used to represent the point with the other 3 values. Okay? So it's something like saying, okay, the point is at 45, 36, 23 measured in inches. The point is at 0.1, 0.75, 0.24 measured in meters, and so on. Okay? So these 4 components represent some sort of scale, unit of measure, that the first 3 coordinates uses to identify one point in space. Okay? So, since we have a 3-dimensional space and we have one point, only 4 coordinates, we have an infinite set of values that would represent the same coordinate in the same place. For example, let us do something very, very simple. Okay? Let us imagine that we want to have one point over here that is on the xy plane. So here we have x-axis, y-axis, z-axis, and it is on z equal to 0. We might say that this point is 10 centimeter on the left, 10 centimeter from the bottom, 0 centimeter in width, and we are using centimeters. Or we can say something, it is like 0.1 meters in one direction, or 0.1 meters in the other direction, 0 meter in the third one, and we are using meter. Okay? So for every point, depending on the units we are going to use, is something different. It might even have, it is 4 inches on one side, 4 inches on the other, 0 inches on the other, and we are using inches. We are quite used of having different ways of expressing one position using different units of measure. And the same is here. Okay? The only strange thing is how we express this final part that represents the unit of measures. Okay? So, as we've said, we have a lot of tuples that represent the same point in space. For example, all these tuples that you see here represent the same point, which might be 4 centimeter, 4 centimeter, and 5 centimeter in the screen. Okay? They all represent the same point. Okay, so the main idea is that, okay, let us focus on one coordinate system. For example, let us focus on meters. Okay, the one expressed in meter will have 1 in the last component. Okay, so this will tell me if I am expressing everything in meter, this is 1. The other will tell the new scale in meter. So 1 centimeter in meter, how much should it be? Well, 1 centimeter will be 0.01 meter. 1 inch in meter, how much would it be? Well, 1 inch should be, I think, 0.025, but I'm not sure that much about that, since I'm not that much familiar with the conversion between meter and centimeter. Okay? So we have one main scale that we are going to use. In that main scale, we put 1 as the last component, and the other will have a different value that express our unit of measure in that particular reference system. Okay? How can we find if the last component is not 1, the equivalent measure in the corresponding unit? Well, okay, so I say it wrong, so it should have been the opposite. So here, sorry, let me erase. I have said something which wasn't correct. So what we're saying is that 1 meter contains 100 centimeter, 1 meter contains 40 inch. Okay, when we are going to find the equivalent value, we simply divide the first 3 coordinates by the fourth. So if we divide 445 divided by 1, we obtain 445. If we divide 6, 7.5s, we divide it by 1.5, we obtain again the same value. If we divide 8, 10 divided by 2, we again obtain 451, and this might even be negative. The last component could be negative, so we might have -8, -8, -10, -2. In any case, when we divide the first component by the last one, we will always obtain 4, 4, 5, 1. Okay? 1. And this is the main conversion between standard 2-dimensional coordinate and homogeneous coordinates. Okay? Okay. And of course, once the last component is 1, we have the actual coordinate, and we can forget about that and come back to the actual coordinate in the 3-dimensional space we are going to use. Okay, conversely, if we have 1 point in our reference 3-dimensional space, x, y, z, the way in which we convert it into an homogeneous screen in an homogeneous coordinate, we simply add 1 extra for component equal to 1. Okay? So, in standard situation, we will use coordinates in which the last component will be equal to 1. But in some cases, as we will see, the final component might have different number, because what will be shown in the following lesson is that if we change this final component that represents the scale, the measuring unit for the elements, we might perform special transformation like the 3-dimensional projection that people do in drawing with very complex work with the drawing aids. Okay? Okay. As an example, should I have this Cartesian coordinate system A equal 1, 2, 3, minus 5? How can I find the equivalent homogeneous coordinate? I simply add 1. Or if I have this value B and C in homogeneous screen coordinate, how do I find the corresponding Cartesian coordinate? Well, it is enough that I divide each of the component by the last one, okay, and the results will give me the equivalent point in the corresponding three-dimensional space. Okay, keep in mind that if this value is less than 1, the position in the space might be larger than the other, depending on what we use. Okay? Okay, so this is the first thing we are going to do. We are going to use homogeneous set screen coordinates, so a set of 4 numbers to represent the position of one point in space, instead of having just 3 coordinates. And this is the basic for computer graphics, and this is also the reason for which all the special instructions that CPU and GPU has to support computer graphics works with 4 component vectors, because coordinates are always mapped to 4 component vectors. Okay? Okay, so let us do one step further and start explaining why we need 4 components to express one point in a 3-dimensional space, and these 4 components in most of the cases will always be 1. Okay, so first of all, let us call what is an affine transform. So an affine transform is a mathematical way of transforming one vector into another. I start from one vector and I obtain another vector, okay? And is very simple, as we will see, can be expressed with a matrix product. So by using this particular type of homogeneous coordinate, we can perform all the typical changes of coordinates by varying by using some simple metrics. Okay, so the idea is that whenever I have one object in 3D, sooner or later I would like to move it. Many of you have done the game design course, know something about games, want to do games, or even if you don't want to do games, you want to do some scientific visualization or whatever. Sooner or later, you will have to place objects in different space of the 3-dimensional space. You might want to rotate them to make them larger or bigger, okay? If you want to move something, you will have to change its coordinate in space. Coordinate measure the position of one object. If the object changes position, the coordinates change. So, a software that wants to move one object in the 3D space must update the coordinates of the point of the object to achieve some special type of movements. Okay? Movements of objects in 3D, that means varying the coordinates of the points of an object, is called transformation or simply transform. This transformation can be quite complex because we will have to move all the points of one object in a consistent way in a 3D space, okay? Lucky for us, thanks to the fact that we have added this extra 4 component to the coordinates in the 3D space, and to a very simple mathematical concept that is called affine transform, we can encode most of the things that we would like to do to an object, to the movement of an object in a 3D space, with a very simple framework. Okay, so objects in 3D are defined by the coordinates of their point. So for example, here we have this strange shape of pyramid in which one point here is in coordinate 0, 0, 1, one point here is in coordinate 0, 2, 0, this other point is in the origin of the axis, and this other is at 3, 0, 0. Okay, this is some sort of object in the 3D space. By applying a fine transformation to this object, we can move it and rotate it in space. So let me just show you the effects that we might achieve. Hopefully this will work. Okay, so movement means that the object is moved in some direction, like in this case. And by applying some affine transform, that object that was in the middle can be changed. But we might also want to rotate it. And rotation can be quite complex because we have 3 dimensions, and so all the points must be rotated in different ways depending on where are with respect to the center. A affine transform can also change the size of one object, make it smaller or bigger, or even deform it to make one side larger than the other. Okay? Thanks to the fact that we have these 4 coordinates, we can perform this single transformation and combine them to transform that original element into something more complex or positioned in a different way. Okay, so this is why we want a affine transform, and this, let's say, showcase what we can do by using simple affine transformations. Okay? Okay, so this is the idea. We want to rotate one object into space using this. Okay, so the affine transformation that can move one object in space are grouped into 4 classes: translation, scaling, rotation, and shear. Okay? And translating, rotating, scaling, or making the shear of one object means apply the same transformation to all the points. If I repeat the same transformation to all the 4 points of this object, I will find the same object rotated of 30 degrees in one direction. Or if I apply the same transformation to this object, I can make it very, very small and move it far apart to the left. Okay? This is what I can achieve with this type of transformation. Okay? And whenever I want to transform a complex object, I transform independently all its vertex, and what I obtain is an object that goes somewhere else. Okay? Is positioned somewhere else. Okay. So, in the following, what we would like to do, we imagine that one object is formed by a set of points P. Each point is characterized, as we have said, by 4 coordinates. So we have the x, y, and z, plus the 4 coordinate w, which most of the time will be equal to 1. Every point will have a set of x, y, z coordinate. When we move it, we might want to have this coordinate being changed. So, for example, let me return here. Let us imagine that I want to move my object slightly to the right, like this. Okay, so this vertex might become 1, 2, 0, this other might become 1, 0, 1, this other here can become 4, 0, 0, etc. Each vertex P is transformed into another vertex P prime. And if we apply the same set of transformation to all the vertex of one object, we obtain the same element shifted, translated, or rotated. Okay? So this is the main idea. We want to have a transformation, something very simple that if we apply to all the points of an object, we are able to move it, rotate it, making larger or making it smaller. Okay? Okay. So, affine transform tell us that we can encode all the movement that I showed in the movie with one single 4x4 matrix. So, movement, rotation, making things larger, making things smaller, can all be encoded with 16 numbers that forms a 4x4 matrix. Okay? If we consider the point in space as a 4-component vector, the transformation is done performing the matrix vector multiplication between the matrix that represents the transform and the vector that represents the point we want to move. Okay? And the result of this matrix vector product will tell us the new coordinate of the object after it has been moved, rotated, or scaled. Okay? So, if we multiply by this matrix all the vertex of one object, we will have a new set of coordinates that will represent the endpoints of the same object in another position in space with another orientation or whatsoever. Okay? So this is the main goal. All the 4 types of movement that we've seen in the movie, well, we've just seen 3, there is a 4th one that we will see in the end, can be converted into a matrix vector product. Okay. One note. Actually, this implementation of using a 4x4 matrix to transform the point of one object can be done using 2 different conventions. In particular, the point is always represented by a vector. The transformation is always represented by a matrix, but the operation that transforms the point, this matrix vector multiplication, can be done by the matrix on the left of the vector or by the matrix on the right of the vector. Okay? Those are 2 ways of achieving exactly the same result with exactly the same thing. However, depending on whether we are multiplying with the matrix on the left or the matrix on the right, the matrix will be different. And in particular, if we are multiplying on the left, we will have one matrix. If we multiply on the right, we will be using the transpose of that matrix, which, as you know, have the row and the column switched. Okay? So, theoretically, is very, very simple. I want to multiply on the left, I have one matrix. I want to multiply on the right, same things, but I will have to transpose the matrix. Why is this so important and why I am telling this to you? You are people in engineering. I think you are used to watch tutorials or read articles if you want to solve some problem. Okay? Well, depending on the source you are using, some will be using the matrix on the left convention, some other will be using the matrix on the right. Okay? That's not a real problem, it's just a question of transposing everything. Okay? We will use the matrix on the left. Why we will be using the matrix on the left? Because this is a university course, which as main reference usually adopts books. And most of the computer graphics books, when explaining the theory, use this matrix on the left notation. However, for the one of you who will try to learn using the tutorial will be based on public available library that do most of the more common and repetitive tasks. Well, the most popular library that creates and handles matrix for computer graphics uses the matrix on the right solution. Okay? So, it might that the standard they will be using will be different from the one that you are used to. Be warned about that. Okay, we will use the matrix on the left. Everything will be done in this course coherently using the matrix on the left, but be warned that many sources that you will be finding online will use the matrix on the right. Just to know it, if you apply a tutorial without understanding what it is doing, if you are using the wrong matrix, usually the result will be a big black screen. Okay, so if you see a black screen, one reason could be that you are using the wrong type of matrix convention. Okay, please be warned about that. Okay. So, before doing a short break, no, let's do a short break, we will do this later.